Hello, anyone? Can you hear me? Yes, thank you. Thank you, thank you. So welcome to week 16, the last week of instruction for lecture A. We are not going to have lecture B, okay? We only have lecture A this week. So this is our last lecture, all right? Let me see, we have enough students here. We have 23. I thought we have more. Okay. Yeah. So as I said, I'm going to do the final exam reviews with everyone. I expect we have 60 students. I only have 20 something. This is the point I don't understand what's going on. Okay. So, well, let's get started. Okay. So let me hide it. So I'm still going to record today's lecture because it's important for everybody to have information on the final exam. So today is what is today? It's the 5th, right? So this is a week 16A, our last lecture, okay? And I probably will extend today's lecture if the time is not enough. I have quite a lot of things to go through. Okay, you are here for me. Thank you. Okay. Yeah, you come. I'm very happy to see you. Okay. So today we plan to do this a few things. As I said in our syllabus, I said I'm going to sensors, actuators. I want to tell you something about IMP, DOB, and PID, all these things. So I need to fulfill that part. Okay. So IMP, DOB, and PID Autotuning. So that's part one. Part two is regarding what I said. For the job market, you need some of the basic skills about LabVIEW, okay? And basic idea of PLC, okay? So when you get a job interview, you can tell people, oh yeah, actually I know. It was briefly covered in our mechatronics class in the end, all right? So that is this part, okay? The third part is regarding a cost evaluation, okay? Evaluation. And some of the surveys, I'll walk you through that, okay? Walk you through that. So shall we start? Let me see how many students we have right now. We got 34, better, very good. I also noticed that every time I have about 40 out of 60. So meaning 1/3 of the people will not missing, okay, will not join me in a synchronized way. So you may have different reasons, but as a full-time student, you cannot always attend synchronously about your lecture. This is an attitude problem and time management problem, as well as self-control and self-discipline problem. I see like that. If you watch the movie, and I checked my YouTube watching times, okay? I can guarantee that many of those who missed the class never actually watched the YouTube. In fact, the number of watches are just averagely so low. So there are some people showing attitude of learning that I don't care. If I don't get past a good grade, I just blame the professor. That's wrong, the attitude. So I'm here to be a fair professor. Okay, I want to make the fairness. If we don't show you, you understand, you don't deserve a good grades. I'm serious, okay? So those are the basic facts about this. So of course, many of you may say, oh, I got solution menus for previous years. So I got solutions, all the homeworks I did perfect. But your final exam, okay? Okay, I'll design it in such a way that you have to show that you have learned, okay? All right, so now let's talk about IMP. This is called internal model principle. We have learned this one already, okay? We talked about system types, okay? System types. Say for example, I have a C of S, I have a G of S, okay? So if I don't have an integrator inside here, say for example, the transfer function in this loop transfer function, loop transfer function is C times G, then I can write a numerator and a denominator. Let's do this one. Numerator and denominator. So if the denominator doesn't have an S, then when you have a step, then you have a response. So you have an E in here. Okay, this is your arrow. So your arrow steady state is the arrow when t goes to infinity. Okay, it will not be 0 if you don't have this one. Okay, so this is called system types. Okay, system type. So so like s to the power of r. Okay, so r is 0 is type 0. Okay, r is 1 is type 1. Okay, so type 1 means you have an integrator. Okay, within the loop. When you have an integrator in the loop, then the steady state error will be 0 for sure. So that's called system type principle. This is only for a step signal. And this is because you have S in here. Therefore, you need a type in here, okay? In here, okay. So what I'm trying to convince you is, in general, if you have a signal, okay, you have a signal, a reference signal, okay? It has a R of S, okay? R of S, and it has a numerator R and denominator R of S, okay? So in our case, if RS is 1, so then NR is 1, okay? Then DR is S. So this DR must be contained in the DL. The DL is, you have a L in here, okay? DL meaning must be contained the DR times the DL prime or whatever. You can factor out, okay? Factor out this. So this is called the generating characteristic polynomial of the signal, okay? So this signal is generated by what? A system with a transfer function of RS driven by delta of t, okay? Impulse response. And the transfer function is dr, nr, So dr is a polynomial, characteristic polynomial. So the characteristic polynomial must be part of or contained in the loop transfer function dl here. Okay, dl here. Or in other words, we can factor out the dr in here. Then you can rest of the things are here. So this is called, we don't have quiz today. We already got 30 of them, enough. So we can factor out this one. So if you cannot factor out the dr from the dl, that means the steady state error will be not 0 if you cannot factor out. So let me give you an example. If you say I have r of t, that is a sine of t, okay? And this is a polynomial Laplace transformation pair of this one, right? And this one. So when you design a controller, say for example, G of S is a DC motor system. So the K over TS plus 1. So I want to ask you, what is the structure of the C of S? Yeah, I tell you, the C of S must be, you have this term, that is the dr, okay, the dr. Then you have AS plus 1, AS plus B. Then you can tune A and B to make overall system stable. In fact, that is also called pole placement. There's a dedicated algorithm to do that job, find A and B. So that is called the format or configuration or structure, let's say, the control structure. So the IMP gave you the guideline how to choose the structure. So this is from the IMP, internal model principle. Okay. All right. So we did the first one, and I'm going to talk about DOB. You have learned this before. There's a week 11 lecture recorded. I only did a 45 minutes talk. We talked 3 things in that lecture. One is MP, and Euler parameterization. And we talk about Smith's predictor, right? In the Smith's predictor part, we did the CGE minus LS and 1 plus CGE minus LS. We figure out a magic way to simply pull out this thing. So the delay will not affect my stability anymore, okay? Okay, so the transfer function, it is like you have G in here, you have minus S in here, all right? So you have a controller in here. So if you do this feedback control, then your closed loop system is CGE, this one and this one, right? No question about it. The Smith predictor is to give you an idea, say, oh, let's do this way, okay? So then you have a G, you have G of S, here you have 1 minus E minus LS. Okay, you do this way, and you do this one, it's minus. So this is a Smith predictor, okay? By doing this kind of feedback, okay, then the closed loop system will be only like, this is CG 1 plus CG times E minus LS. Okay, isn't this like magic? Compare this B versus A. Okay, it's different, right? So that's the beautiful side of Smith's predictor. So the reason why we call it Smith's predictor is from physics point of view, Y is measurable, okay? Okay, so GS, So this U is available, Y is measurable, okay? So GELS times U is Y. This is all physically available signals. However, GS times U, okay? This is U, right? This is U. Then you have GS times U, okay? That is actually is YELS. LS is future, right? Minus LS is past, it's delay. So how this is physically possible? So that's why we call this is, if you need to do you measure the Y and then do a prediction. So you actually, you get this Y, you need to predict what is a T plus L. So that is why it's a predictive control. So this expression, so of course, GE minus LS times U is Y. This is measurable. But G times U, it is not measurable. It's by prediction. Okay. So that's why it's called predictive control. So now let's talk about, I only have 37 students in the class right now. That's, I totally don't understand, okay? So I'm going to do a PID Autotuner. So basically you have a PID control. So you have a plant. You basically have a PID control. You want to do it, PID control. So you have something here, you do this, you do this, you do this. So this is traditional PID control, but from time to time, you probably say, oh, I need to do retuning of the PID. How I do that? What they do is they put a relay element in here, okay? So you turn the switch here to here, okay? So this is switch to here. So then you have a feedback. So this is called relay feedback experiment. By doing that, you are going to see your output will have oscillation, while the input in here is this input in here is like a square wave, only one or minus, right? Minus one. Okay, 1 minus 1. So then you can measure what is the PU, what is ultimate period, okay? You can measure what is the ratio between the output here and divided by 2, right? So this is peak-to-peak amplitude, A divided by 2. This is 1 minus 1 is 2, right? So the magnitude is 2. And this magnitude is A. A divided by 2 is the ratio. So with this ratio, with this PU, okay, with this PU, you are going to use the Ziegler-Nichols tuning table to decide your K, TI, and TD, right? Again, the PID, we usually, when we say PID, we should use this one. It's a K overall, then you have E, okay, and plus you have 1 over TI, you have E dt, okay, plus TD and this dE dt, right? So why this is always true? Because this is time, So the overall, this is the unit like E, okay? So this is a DDT, you have time divided by time. So this is still E, okay? Unit E, okay? So add all this unit E together, then you do a K. That's why you use this one in industry all the time. But in the textbook, many people say, oh, I do KPE, KP, KI, integration of E, and KD, E dot. Is this okay? Yes, it's okay. You can interchange it. But in that case, this KD, KI should have a unit, and this one can be unitless. But this one will carry different units, okay? Yeah. Otherwise, you cannot just add things, variables with different physical units together, right? But how to decide all these parameters? So you're using Ziegler-Nichols. Using Ziegler-Nichols is based on what information? So we did two methods. One is called a reaction curve, right? Reaction curve. Another one is called, Cohen-Cohen is reaction curve. Okay, Cohen-Cohen. Another one is called ultimate oscillation. So meaning you do a proportional feedback control and pushing the gain to a point, the system will start to oscillate. And that will damage the system, right? So you use relay feedback. So your input signal is always limited like this, okay? You're not going to damage the system. So the system will have oscillation. But be careful, you need the formula to convert this one to the ultimate period, okay? So I think we covered this part already. So this one is like a 2A method. It's called relay feedback experiment. So relay feedback experiment. So because relay feedback experiment is safe, widely used in industry, and therefore it can be configured in such a way inside of the controller. You have a different modes. So this is like tuning modes. So this is operational modes, okay? Okay, so if you feel the system is not functioning as satisfactory, fine. Let's switch to here and let it run. Then we can automatically check and retune the PID. Retune the PID. So by turning to tune position, the system will run, and after that you tune back, the PID will be tuned based on that oscillation information. The then system performance is back again. So this whole thing is called auto-tuning, okay? Auto-tuning, okay? Auto-tuner. But people also write PID relay feedback auto-tuning, okay? Relay feedback auto-tuning. So I hope you know this one. In the industry, if you use any of the PID control, you are going to see this, okay, for sure. Okay. So we have done the part one regarding our IMP, PID auto tuning, but I haven't done the DOB yet, okay? So DOB yet. So here's the DOB. Actually, if you go to industry, you are going to see this idea a lot, okay? So let me give you an example. So you have a plant in here, and you have a controller, okay? Yes, everything is running, but sometimes you start to see something this is a disturbance, okay? Not as good. This D will make your system very bad, okay? So how I can cancel out this D? So one of the ideas is you buy a sensor here, measure it, okay? Yeah, measure it, go through some sort of filter, then you add in here, or adding here. So you add in here, that's the physics connected. Then hopefully you can measure it. Hopefully you can measure it. Then, but this one needs extra money to measure it. And most importantly, even you have money to buy a sensor, but you know, in reality, there's no way you can put in to measure it. So you cannot. It's not possible to measure. Okay, it's not just a matter of money. Okay, so suppose you cannot do anything here. Okay, this takes money, and also physics will not allow. Okay, so what are you going to do? You still have this one here. Say for example, you have a pressurized tank. Okay, you have something within the tank. You cannot go inside and measure it. So, but I hope we can compensate something disturbed inside. So what we do is here, this is available to you. Y is measurable. You have sensor information in here. We go through a filter, okay? Hopefully this is P inverse, okay? So then you get a signal like this. So like this, okay? So, but this signal you cannot measure, right? You cannot measure, right? You cannot measure. But this signal, you can assume you can, because you apply to the signal, you know it. So how about we use this one minus this one, okay? Then I have something, the result, I put it here and do minus. So yeah, this is great. In principle, this is great, okay? In principle, this is great. But there are some problems. First one, if there's some error in here, this is not accurate. And here, you probably need another one here. It's called Q. It's a filter, okay, to limit the Q filter, to limit the bandwidth. You don't want all the way compensate. You only focus on some frequency range of interest. So you put the Q in here. But remember, if you put Q in here, it's the same as you put Q in, so Q in like this. Something like this. So you have C in here, you have D in here, you have P in here. Okay, so what I'm trying to say is you have U in here, you go to Q, you also go to a Q. So then this is D hat, this is D, they can minus it, okay? So it's the same. You have a Q in here, you can push the Q inside. So you should have a Q in here and a Q in here, right? Okay, it's the same. So, but this is more realistic because you have a control signal goes through low pass filter here. Say for example, it's a tau s plus 1, okay? So you get this signal. This is totally reasonable. You filter this signal, right? On the other hand, this is more interesting. Okay, let me show you. Suppose that, let me give you an example. Suppose that your P is a velocity loop, is K over Ts plus 1, right? But if you inverse it, you will have 1 over K Ts plus 1. So it's okay, I know, it's okay, I know that 1 over K plus 1 is okay. But this is dangerous. This is kind of like a barefoot. Barefoot. differentiator. Okay, differentiator. We don't like it. And this is relative degree -1. This is not desirable. Okay, so if I put tau s plus 1 and multiply by this one, then this is realizable. It's realizable. Okay, and if needed, even I can put different relative degree here. Like so, my rolling off is faster. Otherwise, so this is 1, this is 2, right? So square, you have faster rolling off for the body part, right? Okay, we have 38 students in the class right now. What if I put all these contents in the final exam? Then you said, I don't know. Then you blame on me, say I'm a bad professor. That's not fair to me, right? So, all right, so I think I'm done. So this whole thing is called disturbance observer. Basically, we're trying to observe this one as a d hat, okay, d hat. This is called disturbance observer, okay, structure. But don't do this way. This is a kind of like idealized, because this is not realizable. You got a noise in here, then the noise here is really high because of this S, okay? Don't do that. So I prefer you put Q in here, Q in here. So this is called idealized. This is called realizable, okay? Realizable. So when I ask you to do DOB, you should do this form, okay? So then your disturbance will get attenuated much more, okay? Much more. This is actually widely used in industry. So going back to the beginning of our plan for today, IMP, DOP, and PID tuning. So next I'm going to do LabVIEW and PLC. It's actually much easier. We just watch movies. So let me do LabVIEW for you. I think I don't even have to go through LabVIEW with you because you know the Simulink. Oh, I got 39 students in the class. I'm very happy. All right, so I'm going to go quickly, give you some preparation of psychological preparation. So at least you can tell yourself, yeah, we briefly covered in the class. So yes, LabVIEW is NI's product. So we can go through this one for about half hour, but let's try to go faster. Okay. So basic idea is instruments, okay, instruments. VI stands for virtual instruments, okay, VIs, virtual instruments. So you know that we have explained in the previous sensor part regarding the sensing mechanism. You have sensing mechanism, signal transmission, then finally you have a display, you present it or store it. All these things now can be virtualized. You don't even need to build the real instrument, just can do it on the screen. But of course, AD, DA, so analog signal, you have to convert to digital signal. And you have digital signal, how you can sample it in DI, okay? So these are the in, okay? Input to the computer. Okay, the computer can also get output. So I have DA, okay? Digital to analog. and DO, digital output. So like digital output, digital input. So let's get some basic concepts up. So basically, this is you have a front panel. This is the panel, and if you remove the panel, what's behind it? It is simply this is like a virtual instrument. In the back, you have a sensor, okay, the real sensor, then interfaced with analog to digital channel. So the front channel, for front panel, you have controls, that is input, indicators as output. Okay, controls like a mode switch. Okay, block diagram is behind. So inside here, so this is the temperature. dBl is a double precision. Okay, so then you have a channel. That means the board ID is 3, channel ID is 0. The number 3 board is, that means ADDA board. Okay, ADDA board. Okay, inside the computer. So then you got a voltage reading in times 100 minus 32 times 9 divided by times 9 divided by 5. Okay, so it's 1.8. And then you will convert the temperature to Celsius. So you have a switch in here, temperature in Fahrenheit, okay, or Celsius, okay. So that is LabVIEW programs called virtual instruments. So basically behind the block diagram, okay. Behind the panel, what is the block diagram, how the components are wired together. And you can see all these operations very similar to Simulink, okay? Simulink. But today, you don't really have to have a board, okay? You can use USB, okay? You can use USB. And then this board will be able to plug into your laptop through USB or desktop USB. So previously, you need to open the computer, and there's some motherboard and slot to plug in. So that's why we call a board an ID. You can have multiple boards to do that. But USB, you can have a hub, so you can have also multiple boards. So this is a board, okay, called signal acquisition. This board, the inside here can be preset about, oh, this signal is connected to the board via which channel to which board. So that is. Then you have a signal manipulation block. They have a presentation block. Is this reminding you our basic signal sensing framework instrumentation? So signal acquisition, of course, before the signal acquisition, you should have a sensing mechanism, right? How you make that one. Turn the physical quantity into the voltage signal you can sample. Then presentation. So user will look at this panel, okay? Look at the panel. So the front panel sends control data also, like true or false. Like this is like a toggle true or false, C or F. By doing that, you can use different modes. Okay, so this is called DI, digital input. The yes or no, 1 or 0 input. Okay. All right. So there are a lot of things similar to the Simulink. It's use different libraries for operations. So and also can put a waveform graph into this. Okay. You can also do a stop, start. You can do integrate. You you can do this temperature display. So this display, or you can use another display, waveform graph. There's a panel toolbar. So all these things already built in for you to construct a nicer specific interface. Okay. Okay, so even you can include the while loop inside. So you have a stop loop, loop button, and so on and so forth. You can also do a subroutine called sub-VI, okay, sub-VI. So there are a lot of concepts are parallel to a Simulink, okay? Simulink, you have masked subsystems, okay? And these are the palettes. I call this is a library of controls and functions, different types, okay? I don't want to go through that. You can, these are the status toolbar, how to do the programming, and so on and so forth. So it is actually very interesting. So in fact, LabVIEW is not a view; it's a virtual instrument, and so the E and W stands for this is a workbench. I remember. What is the E? I need to find out. Okay, virtual instrument, experiment workbench. Yeah, maybe. This is similar to the Simulink wire connection. So why would do that? And they can use this one to mimic some commercial panels. If you buy an oscilloscope, then there's a panel, right? So they also have that with you. So sub-VI is, no, it's not important. It looks very, so you can reuse of those sub-VIs. And many of the sub-VIs, they probably already presented to you. Data acquisition is, I already said, is a DAC device. It's a board. You can see the bus and plug into this. But today you use USB. Don't use the slot and plug in. So of course, this is very important to connect to the sensors. So you have sensors through the wire connection to the terminal blocks, and you have cable linked to the board plugged into this. So this is how you make the sensor going through the computer and displayed. You have a panel. So here you have a panel. Okay, it's like a VI virtual instrument panel. Okay, then together it's like a sensor to the visualization. So that's why it's called virtual instrumentation. I think I gave this deck of slides in the. Yeah, this is something you can see. This is a computer. This is a terminal board. Okay, terminal board. This is a power supply. You have electronics. You have sensors here, and the ADDA card is plugged in the computer. Okay, inside of the computer. You're not seeing on the CPU computer. So you have different ways of monitor of this. Okay, this is a LabVIEW-based. So this is a photobioreactor, light sensors, power transducers, terminal block, and DAC hardware in here. Okay, the linked all the wiring here. So this is the monitor. This is the PC. Inside of the PC, they plug in the ADDA card. Okay, so then you only interact with this interface. It's called virtual instrument. So this is a typical LabVIEW application scenario. I hope you, so inside here, you can keep this photobioreactors always under control. because everything you can sample and display and see whether they are in a safe region or unsafe region. So it's you monitor all the real-time data, temperature, and so on and so forth. Okay, so where do I go from here? So I would like to say, if you are giving a VI project, ask you to do it, you should have 100% confidence, say, yes, I can do it. Just spend time reading the menu and play around, like you get familiarized with MATLAB Simulink. I think this digital twin last project is helping you to gain that confidence. Okay, so I'm going to finish this part. Our timing is great. What I'm going to do next is regarding what I'm planning to do, LabVIEW and Programmable Logic Control, PLC. In the industry setting, I hope that because the plants, okay, they are in different places. So usually you hope to make a central monitoring room to do that. So let's go through, watch some of the distributed control systems and programmable logic control movies, then get familiarized with that. So
the earliest form of computer-based control was called Direct Digital Control, or DDC. Early DDC replaced standalone controllers with a central computer. All measured process variables were sent to the computer, which was programmed to carry out all process control tasks. This centralized control function made communications between loops possible. Unfortunately, relying on a centralized computer had a major disadvantage. A computer malfunction could cause the entire system to go down, necessitating the need for expensive redundant computers or a backup control system. The earliest form of supervisory or setpoint control combined the advantages of single loop and direct digital control. Like direct digital control, supervisory control was structured around a central computer. The central computer generated controller setpoints for the individual loop controllers. However, all final control actions were carried out by the controllers.
Local controllers, yeah.
Supervisory control incorporates the advantages of DDC, but is more reliable because the control functions are contained in individual loop controllers. Supervisory control systems can still be found in some facilities. Supervisory or setpoint. The development of distributed control systems, or DCS, was made possible by solid-state electronics, electronic circuit miniaturization, high-resolution displays, and data communication. A modern DCS is a collection of microprocessor-based modules that work together through a real-time communication system to control and monitor the process operation. The DCS carries out rapid communications between modules via a data highway. The DCS receives signals from field devices and uses them to control loops, execute special programmed logic, monitor inputs, alarm plant operations, and trend, log, and report data. DCS combines the reliability of standalone control with the computerized capabilities of DDC. Each DCS module is a microcomputer that is dedicated to specific functions. Process control may be distributed both geographically and functionally, and control subsystems are only responsible for controlling a portion of the entire process. One advantage is that if a control subsystem fails, the only loops directly affected are those controlled by that individual subsystem. The rest of the process will remain under control. To prevent any loss of distributed control.
So that's give you an idea of DCS. So Mechatronics system is only part of the larger distributed control systems, okay? And they are connected through the field buses. So let's go to Yes, actually, let's go to a single
On-off control is a basic form of industrial process
turn off,
control.
turn on.
With on-off control, the final control element has two positions. Let's take a look at how on-off control can be used to control the level of liquid in this tank. Fluid is constantly being fed into this tank. The set point is 50%. If the level falls below 50%, the valve closes to raise the level in the tank. If the level rises above 50%, the valve opens and processed fluid is discharged from the tank. In this system, the final control element, the valve, has two positions, fully open and fully closed. Since on-off control usually results in oscillation, it is only used in processes that can tolerate deviation of the controlled variable from the set point. On-off controllers may also have an adjustable dead zone or dead band. The dead zone is a range of values around the set point. No control action is taken if the system remains within the range. This helps prevent wear and tear on the equipment. On-off
So proportional control.
Proportional control provides continuous control in a process that requires little or no deviation from set point. In a proportional control system, the output change is proportional to the input change. The output signal from the controller can position the final control element at any point between fully open and fully closed. Control action in a proportional loop can either be reverse or direct acting. In a direct acting control, as the input signal increases, the output of the controller increases. With reverse acting control, as the input signal increases, the output of the controller decreases. Different processes have different process dynamics. Temperature is a process which has a slow response. Flow has a very rapid response. Controllers must be adjusted to compensate for process dynamics. This is done by adjusting the width of the proportional band. Proportional band determines the amount of input required to provide a full range of output. Adjusting the proportional band on a controller to provide the proper response is necessary to stabilize system operation. For example, if a fast-responding process were controlled by a controller with a narrow proportional band, the process could become unstable, resulting in oscillations. Likewise, a slow-responding process controlled by a controller with a wide proportional band could result in sluggish system response. Proportional control integral or reset action is added to proportional control to eliminate offset and return the process to set point. Integral action repeats the proportional output over time. As long as the offset exists, the integral unit will continue to act on the controller's output. Therefore, the integral action responds not only to the magnitude of the offset, but also to the duration of the offset. Units of integral control may be expressed in repeats per minute, often abbreviated REP, or minutes per repeat, often abbreviated MIN. Although integral control can overcome offset, often a load change will cause the controlled variable to rise above or below acceptable limits before the final control element can be adjusted enough to make corrections. In this case, derivative action may be added. The derivative action senses how quickly the process variable is moving away from set point and anticipates the overshoots based on the rate of change. Derivative or rate action will immediately add to the controller's output signal to minimize overshoots. Derivative action is most often used when rapid response of the controller is required.
So there are advanced controls, including feedforward. After that, we look at the PLC, okay?
Because a feedforward system usually monitors several variables, it's programmed with a mathematical model that predicts how interaction between variables will affect the process. This model determines the proper amount of control action to maintain the controlled variable at a consistent value. Because of the difficulty in predicting exactly how these variables will affect the process, feedforward is seldom used alone. A feedback loop is usually added to the feedforward system to monitor the effect of the control actions on the controlled variable. As in any PID-controlled system, In a feed-forward system, the value of the controlled variable is determined by the set point. The response to a set point change in this system will be similar to that of a feedback-only control system. Feed-forward can be found in processes that are difficult to control, like boiler feed water, direct-fired heaters, and distillation columns. Because processes that require the blending of two continuous flows in precise amounts can use ratio control. A ratio control system monitors the rate of one flow and sets the rate of a second flow at a specific ratio to the first. For example, if the ratio selected was 2 to 1, represented on the controller as 1 to 0.5, the flow rate in line B would be equal to half of the flow rate in line A. A ratio control system is used in processes requiring the accurate blending of two or more continuous streams. A ratio control system is often used in batch reaction processes or to control the ratio of airflow to fuel in a boiler to ensure efficient operation. Ratio control can also be found blending ingredients in the food processing industry.
So selective control.
Selective control is often used to override normal control and take corrective actions before hazardous conditions cause a shutdown of the process. Selective control can also be used to protect against instrument failure. In hostile environments where transmitter failure rate is high, a signal selector is used to choose the median signal from several redundant transmitters.
Okay, here comes to our core part regarding PLC. So PLC, most likely you are going to use it in the industry environment very often. So let's get some basic ideas.
Programmable controllers are industrial computers that can be used to control machines or processes. They perform functions once done by electromechanical devices. Because programmable controllers have fewer moving parts than hardwired systems, they improve efficiency and reduce maintenance. Programmable controllers, or PCs, are designed to withstand rugged industrial conditions. Because of their versatility, reliability, and efficiency, programmable controllers have become an industrial standard. Programmable controllers are typically used in manufacturing to control automated machinery, such as this burnisher. Programmable controllers are ideally suited for machine control applications because they are reliable and cost-effective. Here's an example of a typical application of a programmable controller in a process. In this process, the PC controls valve sequencing, mixture operations, pump operations, recirculation, and tank temperature control. Whatever the application, a PC system performs three basic functions. It receives information, makes decisions, and specifies actions to provide control. Field devices communicate the conditions in a controlled process to provide the PC with information. The PC compares the information with the instructions in its program to make control decisions. Other field devices convert an electrical signal into a mechanical motion. In this way, a PC's decisions become actions. Here's
Nice.
an example of a typical
Okay, nice.
information, decision, and action functions in various PC systems are performed by similar basic components. However, the size and configuration of the system may change. Information about the process is provided to the PC by input devices. Examples of input devices include switches, push buttons, sensors, and thumb wheels. There are two basic types of input devices. Discrete input devices have two functional states, on or off, open or closed. Analog input devices, such as this position transducer, send signals which range in values. A programmable controller, like any other computer, must be given specific software instructions to control machines or processes. The ladder logic of the user program provides this set of instructions for the PC. Because PCs originally replaced hardwired relay circuits, PC ladder logic was initially developed to resemble conventional relay logic. Even today, PC user programs use symbols that resemble relay logic symbols. A brief review of relay operation may help you understand PC software convention. A programmable controller uses software to perform control functions. You must have a working knowledge of the user program to troubleshoot control problems. As you can see, the structure of the user program resembles a ladder. That's why it's called ladder logic. Like a ladder, its basic structure is made up of rungs and rails. Power rails are found on the left. Power flows left to right through rungs. Rungs originate from the power rails and are usually numbered from top to bottom. This allows for cross-referencing when troubleshooting within a program.
So, see two examples.
This symbol represents normally open contacts. Contacts are used in the program to represent many different types of real-world input devices or internal outputs. The contacts are referenced to an address. When the referenced address goes high, normally open contacts will pass power. This is the symbol that represents a normally closed contact. A normally closed contact symbol can represent a real-world input or an internal output. The contacts are referenced to an address. When the address they are referenced to goes low, normally closed contacts will pass power. This is the symbol for an output in ladder logic. It's often referred to as a coil. The output can represent a real-world device such as a motor starter, or the output can be used to operate contacts in the ladder logic as an internal output. This is the symbol represents a function block. Function blocks perform special operations such as counting, timing, math, or data transfers. Function blocks allow the programmable controller to perform functions that go far beyond the capabilities of relay logic systems. This symbol
So we watched all these industrial distribution control systems. I think you guys are ready to get into the real industrial environment. But we do have pretty lengthy, not really, it's a 12 pages of long programmable logic PLC lectures. That part I'm going to skip. We need to spend some time to do a review. As I said, we will continue this lecture after we finish this part. Any questions at this point? Let me see. So basically, let me review what we have learned, okay? So we had basic idea of mechatronics, talk about basic elements, generalized the components and its connections, and using linear graph to write down their equations. So, and especially in the components part, we put a lot of emphasis on op-amps, okay? After that, we to pick up concepts on signal systems like Laplace transform, like convolution transfer function, okay? And the time frequency domain response, okay? And doing modern simulation, okay? And in here, especially we talked something called realization. So you are giving a transfer function, you are giving some op-amps and resistors, capacitors. You should be able to construct simulator of this transfer function. Then control system, we talked about basics of the stability, the system types, steady state errors, body plots, so on and so forth. In particular, we put the PID control in here, okay? And then we spend time on the sampling process, sampling theorems, and like aliasing, Z-transform, initial value, final value theorem, and discrete equivalent design, and so on and so forth. Then we talk about motion sensors, basic ideas of sensors, 5 different specs, okay, in the table for the sensors, actuators as well, okay. Then today we talk about these things, okay. So I've done the reviews, and what's next is regarding something I want to show you here. So we just created this morning and did sensors actuators. So you can see in 2020, so all these are the submitted, all these are submitted slides for the last year. I'm also putting last year. So including this year, this will be yours. I'm going to put index file like I showed you before. This actually can be accessed from our Mechatronics labs website called Lab Resources and Lab Resources. So these are all 8 years. 1, 2, 3, 4, 5, 6, 7, 8. 8 years of that. So you can see this is 2005. So different people with different sensors actuated. I'm trying to make up a web page index for each year. And over the years, you can see we accumulate so many different sensors actuators. Okay, so please make yours in an impressive way, because everybody in the world would be able to see your work. Okay, you don't want to put evidence that you plagiarized others. Okay, don't do that. Also, you need to give source or credentials to all the possible sources you cited. Give credentials to others when you cite, use other people's stuff. I also have a web page in here. So I gave this link in the announcement. So if you are not very familiar with some of the topics, signal and the systems and the circuits, your circuits are not that good. So you should work on, this is a 1 semester contents. For each lecture, we give one very specific example, like Norton Davidson. So this is solved problems for you as a reference, okay? As a reference. I understand you guys didn't do very well about sinusoid steady state using phasor, the sinusoid steady state. You can ignore that part, not a big deal, okay? Digital twins, we are trying to put, you guys are the first year using digital twins in the lab. So we'll put you here and show the world that in this course, we did this. Another thing I want to go through with you is announcement. Listen carefully, please, here. So it's called Digital Twin Surveys. If you click this one, okay, so the first one you click it will ask you to get an overall survey of this class before and after, whether you feel like you have learned, okay? That's very simple questions, okay? Please do that survey, okay? There's another survey. It's not considered as survey. It's an evaluation, okay? It's an evaluation. So I'm not sure which team you are. You know which team you are, right? You click say, oh, I'm evaluating this group, okay? Then I say how they are doing, okay? It's clear or not, so you can complain, okay? So, but if you say, oh, I'm on project, I'm on this project, so it's called App 1. So then you are supposed to give evaluation feedback to team 9. So you should do this way, right? So people, the members of suspension team should choose number 9 to give feedback, okay? So then it's kind of grading to each other, okay? All right, thank you. So you should do that. I think 1 is enough. So at least somebody will review your work. And make sure your work is working. If not, ask Furkan or Harold to help you. So in the next time, I'm going to spend it to, I'm going to stop sharing. I'm going to stop the recording.